My name is JD Bean. I am a principal security architect with the EC2 team at AWS. And in that role, I get to work side by side with the product and the engineering teams responsible for EC2, and particularly for the Nitro system. I appreciate you all coming to join us here at Inforce over the last few days, and in particularly appreciate you joining me for this last session of the conference. So today, I'm going to start off by talking a little bit about something called the Ship of Theseus. Theseus was the legendary founding king of Athens, and in the years following his death, for decades and even centuries, right? So says the story that Theseus' ship was sailed every year on a pilgrimage in his honor. And over all those decades and centuries, the ship was slowly repaired and revised and modified such that not a single physical component of the ship remained the same. It was an interesting thought experiment for philosophers to pose the question of, was this Theseus' ship, or was it not Theseus' ship? Now, I'm not a philosopher, and I'm not here to answer the question, but I think that there's an interesting parallel in this story to the story of the development of the Nitro system itself. So, quick show of hands, who all here is familiar with the Nitro system before? Who's heard of it? Okay. Good to hear. We're going to go into a bit of the nitty-gritty of the security design. I'm going to give a high-level overview and kind of dig deeper and deeper into the system. So at a high-level overview, some things to know about the Nitro system. We launched the Nitro system in 2017, but it had actually been in development since 2012. And we've, of course, continued to refine and develop the system in the years that have followed. The Nitro system is characterized as providing the fundamental and underlying virtualization system for EC2 instances, and is composed of tightly intertwined, purpose-built hardware, software, and firmware. It contains a hypervisor that was built by AWS based on KVM specifically for use within this system. And it's now on its 5th generation of custom silicon chips that power the system. Critical to understand about the Nitro system is, even if you haven't heard of the Nitro system before, if you've used EC2, there's a very good chance that you have interacted with the Nitro system in a sense. All instances that we have launched, all EC2 instances that AWS has launched since 2018, are built on the AWS Nitro system, even a few that we released in 2017. So let's talk a little bit about the journey of how the Nitro system came to be. So pictured here is in fact not the Nitro system. It is a Xen-based virtualized instance, right? The virtualization system that we used prior to introducing the Nitro system and still support today. Now, this was a system that did very well for us and did very well for our customers in delivering value and maintaining a high security bar. However, we ultimately did look at the system and see room to continue seeking innovation, further improvement, and generally raising the bar on both security and performance in the name of delivering value for our customers. Obviously, this is a security-focused event. You all are a security-focused crowd, and a lot of this presentation is going to focus on the security benefits of the system. But it is important to note that there are also massive performance benefits as well. So, looking at this system, we have a few critical components I'll call out. The orange boxes are the customer instances, the EC2 instances that are virtual machines running on a physical system mainboard. But we've also got a lot of other software components there. There's the Xen hypervisor itself, the hypervisor being the fundamental critical kernel core of what makes a virtualization system a virtualization system. In addition to the Xen hypervisor, there's also a special virtual machine known as DOM0. And DOM0 plays a really special role in the additional heavy lifting that makes a virtualization system useful to customers. Things like input, output, networking, storage, and management, security, and orchestration. The Zen hypervisor can be relatively slim in what it actually needs to do, and we'll probably talk about that a bit later in the presentation. But DOM0 itself is a general purpose operating system. In our case, a copy of Amazon Linux. And it contains all sorts of components, right? Things like device models and device drivers to translate external physical hardware into virtual representations for the instances on the system. We looked at this and we saw room for improvement. Particularly in the case of performance, we saw room to accelerate these functions on special purpose hardware, removing this weight from these expensive server-grade chips, things like Intel, AMD, and now even Graviton processors. So in 2012, we started out with moving off the VPC networking functionality into a separate component. And that component, which we'll learn about in a bit, is the Nitro sort of domain of the system. So we found we had a lot of success with this. Customers derived value. They saw improved performance, improved value. And generally, we felt that we were really onto something. So we decided to target the next component that made sense in the system, and that was EBS storage. EBS storage is network-provided storage, so there's a lot of similarities here. It simply it is ultimately working on the network on the outside and presenting a storage device on the other end of the interface into the customer. So our next step was to move our Amazon EBS features off of the system mainboard and into this new and separate domain. From there, we moved to the local storage, right? This is local drives that are attached to the same physical server that is also running the instance and is supported on some of our instance types. Our next step was to relocate some of the management, security, and monitoring features over onto this domain. And this led to the last step in the evolution of the Nitro system, bringing us to its 2017 release, which is we fully removed DOM0, we fully removed the Zen hypervisor, and we replaced it with this new Nitro hypervisor, which was custom built to take advantage of these new properties of our system. Now, we're going to talk in greater and increasing depth about exactly what this system is, how it works, and the resulting security properties. But this was the basic evolution. And looking at this system in 2017, we saw that something had fundamentally changed. We had gone through and re-engineered, from a design standpoint, every major component of our EC2 virtualization system. The hypervisor was different. The fundamental software providing our I/O features and management, security, and monitoring had all been changed, relocated, and moved, converted into hardware-accelerated offloads. And looking at the system, it was still the EC2 that customers knew and hopefully loved, but it was also something new. And so we gave it a new name, and that name was Nitro. And so all instances following this release are specifically denoted and documented as being based on the Nitro system. Even though prior instances benefited from some of these design attributes, when the system as a whole functions together, it has different and special innovative properties. So let's dig a little deeper into what these components are for the Nitro system. And there are really three of them, three categories. The first is the Nitro Cards. This was the left-hand side of the picture we showed earlier. The Nitro Cards are independent systems on a chip, really. Special purpose hardware designed from the ground up by Annapurna, our in-house silicon development team that started our relationship, actually, working on Nitro, came and joined Amazon as part of our company, and has actually not only led the continued development of the Nitro system, but also our Graviton chips, Trainium, Inferentia, our Aqua accelerators, and more. These Nitro cards have their own CPUs, their own memory resources, and are connected on the same PCIe bus as the system mainboard, but are separate, self-contained systems otherwise. And these provide the local NVMe storage, the elastic block storage, the system controller and hardware root of trust, and of course the VPC networking. The second component is the Nitro Security chip. And this is a special custom-built microcontroller that is integrated into the motherboard itself and is responsible for providing protection and integrity monitoring of the hardware resources on the system mainboard. We'll talk more in detail about this in just a bit. Last is the Nitro Hypervisor I mentioned. This is designed as an extremely minimized and lightweight piece of software. In fact, you can really think of it in many ways as firmware. It provides the bare core functionality of virtualization, which is to allocate and break up memory and CPU resources and assign them out to virtual machines. In the virtual machine's day-to-day operation, the vast and statistical majority of instructions do not require involvement from the hypervisor at all. User space code does not require engagement with the hypervisor. It's really only when you deal with privileged or sensitive instructions that the hypervisor has some responsibility there for managing some shadow state. And we can talk a bit about that, once again, as we begin to get deeper into these. But let's start with diving into the Nitro Cards. So these are the Nitro Cards, at least an array of them. And as I mentioned, the Nitro Cards have evolved over time. Variants have been developed for particular use cases and configurations to match our growing selection and options in the EC2 fleet. All of them feature chips developed and designed by Annapurna, and ultimately, as I mentioned, really function as a new hardware-driven virtualization system component. The Nitro chips, the Annapurna chips that power these cards, as I mentioned, have also gone through a great deal of refinement and continued development. Pictured here are the first 4 generations of that Nitro card, and we recently announced, Nitro chip, and we recently announced the 5th version, which compared to its predecessor offers twice as many transistors, 50% faster DRAM speed, and 2 times more PCIe bandwidth, which ultimately translates into increased performance and functionality for customer instances. Now, Nitro cards, ultimately, in every server, we're going to have at least one, possibly more than one, Nitro card. And the Nitro cards together perform 4 core functions. There's the VPC functionality and card that provides interaction with the VPC data plane and a interface for a network into VMs. We have the EBS data plane, which exposes its own interface into the VMs. We have the instance store, which provides its own instance between local disks attached to the server into VMs, and a particularly special card, I like to call her the queen, the Nitro controller card, which really performs a couple of functions. And that is the provision of a passive API endpoint and the fundamental coordination of all of the other Nitro system components. So what do I say when I talk about providing an API? So the Nitro controller really presents the sole outward-looking management interface to what we'll call the EC2 control plane network. Right? This is the private network that underlies our physical facilities and that EC2 runs within in the physical server sense. And when I say EC2 control plane, what I'm really describing here are the control planes for both the practical EC2 service, but also VPC and EBS. Now, these APIs that are exposed by the Nitro controller are very clearly and ubiquitously authenticated, authorized, and logged. And the control planes, which are made up of a multitude of microservices that underlie EBS, VPC, and EC2, are given a least privileged scoped down authorization for only the set of operations that they need to complete their fundamental business purposes. Now, because this interface is so critical to the security properties of the system, we've also invested and worked with our automated reasoning and provable security teams to provide formal verification of the memory safety of this interface over, as a mathematical proof over any and all configurations and network requests. The other category of cards are the Nitro Cards for I/O, which we've talked about. Right? This provides a nice summary of, on the one hand, the functionality that is provided on the Nitro Card, things like for VPC encapsulation, which translates your customer IP packet in your VPC and encapsulates it with information for our network and software-defined networking layer that we've built from scratch. Right? Your IP packet will go out of your interface over to the Nitro Card without need for modification, and is then wrapped with information and encapsulated with information about the Elastic Network Interface that sent it, the VPC that network interface is in, and the Elastic Network Interface and VPC of the destination that it's seeking. And then, of course, on its furthest outer layer, you'll have the IP packet for the actual physical network. All of this is provided in hardware using these custom accelerators, and is provided transparently to your instance. There's no software to change. It all is simply offloaded from the system mainboard entirely. Right, we're also offering some encryption features, which we'll talk about in just a bit. Enforcement of things like security groups occurs on this Nitro Card. Limiters, routing, and a variety of other network-based functions are provided by this card. For the EBS card feature, we've got, once again, encryption, as well as the communication with the back-end EBS servers using our EBS protocol to access remote network storage and present it as a local physical NVMe device to virtual machines. With EC2 instance storage, we've got similar encryption limiting factors as well as drive monitoring for the locally attached drives that is once again transmitted through and presented as an interface to virtual machines as a local NVMe-based block drive. So this is a bit of a view of how this all works, right? As I mentioned earlier, on the bottom there we have the PCIe bus of the underlying system that the Nitro Card shares with the system mainboard. The EC2 instance in the center here is running and has actually a direct connection back to the Nitro Card. And this is achieved using a technology called SrIOV, Single Root Input-Output Virtualization. Essentially, this is hardware-based virtualization of a physical device. So the Nitro Card itself actually is creating and presenting virtualized interfaces that can be passed through independently to different virtual machines without transiting through the hypervisor at all. The initial connection is established, the hypervisor steps out of the way. So let's talk a bit about the encryption that I mentioned, because I think as a security community, this is a particularly valuable feature of this Nitro design. So all three of these devices are providing encryption key storage and transparent hardware encryption directly to customer instances without any involvement. So for example, the encryption keys that are used for EBS and local instance storage, and even for VPC network encryption, which allows transparent encryption between supported instance types, which are the majority of our instance types, are only ever present on the system in plain text when they are stored within the protected memory of one of these hardware Nitro Card devices. The ways in which these keys are generated and managed do have some differences, and we could talk a little bit about that. So for Amazon EBS, a lot of the difference here really comes down to the simple fact that an EBS volume has an independent life cycle, not to mention the ability for snapshots, from the instance that it is attached to. Right? A volume can be detached from a particular instance, can be reattached to a different instance. There's even a multi-attach feature. So because this is a long-lived resource and one that is separate from the instance itself, it's actually managed using key management features from AWS KMS. If you're using the default KMS key storage, that's a FIPS 142-level 3 validated HSM with a key that you as a customer can choose to manage and control. The instance storage, however, is very different. The instance storage is something that is linked with its lifecycle directly to the instance itself. So when the instance shuts down, the volume disappears. So for these keys, we actually locally generate them on the Nitro card that is providing this local instance storage feature. We maintain them for their life in plain text inside that device, and then delete them upon instance shutdown. VPC encryption is another interesting one. Because this is something that is supported between two compatible instance types in the same VPC or peered VPCs when they communicate directly with each other, this is something where we need key material that is available on these other devices. In order to achieve the security properties of the system, what we actually do is to distribute seed materials on a regional basis. Those seed materials are securely distributed, and they are provided to the Nitro card device that is providing the VPC connectivity, and then derived on that device. Those seeds are rotated frequently. And so you can see there are different models that fit to the specific use cases, but the commonality is the ability to provide encryption that not only is transparent to the customer, but is also entirely separate from the hardware on which they're running their specific instance and workload, their code. Next up, we'll talk a little bit about the Nitro Hypervisor. So as I mentioned, this is a KVM-based hypervisor. We've done a great deal of work in customizing and tuning, of course, this custom-built firmware-like hypervisor for this particular use case. We've gone to great lengths to minimize the user space and achieve what we call a quiescent design, which really means that the hypervisor shouldn't execute at any time unless it is on behalf of the instance that is running on those resources. We're going to talk for a little bit. I promise I wouldn't go too deep into performance, but this is actually an interesting area to talk a little bit about the performance characteristics of the system. So it's hard to capture what it means to deliberately minimize a thing in a way that is easy to convey. Metrics like lines of code or something like that aren't particularly useful, I find. What I think is really useful here to talk about is some of the things that the Nitro Hypervisor just simply doesn't have. It lacks anything like systemd or any kind of networking stack, general purpose file system support, peripheral drivers, SSH servers, shells, or anything of the kind. What I think is fair to say is that the Nitro Hypervisor is not a general purpose computing system. It is very much a purpose-built, firmware-driven tool that is really designed to simply perform its primary functions and then step out of the way. So what are those primary functions? First, the hypervisor is going to listen on the PCIe bus for management commands from the Nitro controller. Things like start up an instance or stop an instance. It's going to partition memory and CPU resources, things like VTD, VTX, using hardware features of the various CPUs. That could be, as I mentioned, Intel, AMD, or even our own Graviton chips. Partitioning out those resources follows then with assigning the SrIOV virtual functions that I mentioned earlier, provided by the Nitro hardware cards, and passing them through to the appropriate virtual machine. After that initialization step, that's where the hypervisor is going to step away and really only execute in those limited cases where one of the instances is attempting to call a privileged CPU instruction that's going to trigger the need to manage a little bit of shadow state for the underlying virtual machine. As I mentioned, the vast statistical majority of executions on the CPU are simply happening directly between the virtual machine and the CPU. So the hypervisor is what fundamentally allows us to achieve this diagram, right? This is what allows us to run two EC2 instances on the same hardware, right? Each of them having their own independent connection back to the Nitro cards that is both independent of each other and of the hypervisor. It also allows us to do something rather revolutionary, which we announced in 2017 along with the Nitro system, was the ability to actually remove the Nitro hypervisor from the Nitro system entirely. I like to think of it as having a bit of an asterisk, right? It's a very important feature in a large number of our EC2 instances, but sometimes it's actually not required. Because the Nitro hypervisor provides such a minimal feature set and is really focused only on the dividing of CPU and memory resources among virtual machines, if a customer wishes, we're happy to provide access to a bare metal EC2 instance where you're running directly on the CPU with no hypervisor whatsoever present on the system, and benefiting, for all intents and purposes, from the same type of experience as running on a standard EC2 instance. You don't need to change your AMI image, your Amazon machine image for booting your system. The drivers remain the same, the experience remains the same. The only difference is that the Nitro Card is no longer using SrIOV, but is simply communicating directly with the bare metal instance over the PCIe bus. So this is the one that I promised you I wouldn't do, but I'm doing anyways, which is really the performance comparison here. And I think that the reason I want to demonstrate this is that I think it speaks to the minimal design of the hypervisor itself, right? This compares in a few HPC benchmarks a C5N 18 extra large, a Nitro-based virtualized instance that takes up all of the resources on the particular hardware that it runs, and a C5N metal instance, which runs on the same hardware, but without a hypervisor. As you can see, the performance differential is nearly indistinguishable between the two. So moving on from the topic of the hypervisor, let's visit the last of the fundamental components, the Nitro Security Chip. This is that custom microcontroller that traps all I/O non-volatile storage rights, rejects them. And it's also used by the Nitro controller to kind of extend itself as the hardware root of trust for the system. So a typical system, in addition to storage devices and CPUs and memory, is going to have a few microcontrollers on it, things like, and storage devices, things like BIOS, BMC, various other small devices that are going to generally need to have some firmware, and that firmware is typically stored on a flash device. And when you need to do some update to a firmware on a system, you're usually going to boot that system up and run a utility to write to those flash devices. Now, in a cloud environment, this is something that we want to very, very carefully monitor and control to make sure that only authorized updates are ever going to be flashed to any firmware on the system. When there's a hypervisor running, that provides one mechanism for preventing a customer instance from ever having access to write to non-volatile storage on the system mainboard. However, in the bare metal variant of EC2 Nitro, customers aren't running with a hypervisor, and they're running directly on that bare metal. So one of the key features of the Nitro Security Chip is its actual ability to sit on the bus between the CPU and all of those non-volatile storage devices, so that all writes coming from the instance are simply dropped and rejected. This allows us to protect the local hardware even from the AMI that is running on the bare metal. There's also an additional really critical feature that the Nitro Security Chip plays, and that's really at that boot process that I mentioned earlier about the Nitro controller. So one way to establish the integrity of a system as it's booting is to use the system itself, really, to validate, using something like UEFI Secure Boot. And that is a perfectly fine system, but one that involves hundreds of thousands to millions of lines of obscure C code, and ultimately is kind of rooted in a legacy approach. What we looked at in the system, seeing that we had moved all of the command and control off of the system mainboard, was that we had an opportunity to actually delegate to the Nitro controller not only the sole ability to update firmware on the system mainboard, but also the ability for the Nitro controller to feature as a radically simplified hardware-based root of trust for the system. So on boot, the Nitro Security Chip holds the main CPU in reset and allows the Nitro controller to come in and to read and validate that all of the firmware on the system is as expected and approved for operation before bringing the rest of the system up. It also takes from the Nitro controller's personal and dedicated local storage device a known good copy of the Nitro hypervisor and injects it onto the system. This is another way in which the hypervisor is really treated and managed much like firmware. So obviously the system integrity here is really important to us. And we took a lot of steps to both invent and to simplify in the development of maintaining a secure root of trust here. I mentioned earlier Proofable Security and automated reasoning. And this is another place in the Nitro system where we see this particular approach yielding really positive results for us. Going down to the basic low-level early boot stage code on the Nitro controller, we've gone through formal verification processes to ensure that the system as a mathematical proof is memory safe. And on our newest Nitro cards, we have a really interesting boot chain where the low-level boot code, this proved secure, memory-safe code, builds up through a measured boot process to a TPM-like device, allowing it to decrypt an encrypted local storage device and inject the hypervisor, tracing back all the way from the system mainboard all the way down to this low-level boot ROM. So let's put the components together and see a bit of how the system functions together. So I'll go with a simple example to start, and then we'll get into something a little bit more nitty-gritty. So the first is just launching an instance. So for starters, somewhere out there is a customer. They have to have some IAM credentials that are authorized to perform the action of starting up the EC2 instance. And they need to have an AWS SDK to make a request, or CLI, to make a request to run the instance. They'll type in AWS run, so AWS EC2 run instance. They'll probably specify that the instance type will in this case be an R6GD, which happens to be an instance type that has a local instance storage. And they'll also need to provide a couple of other details, of course, the availability zone, the region, the AMI they want to boot from, etc. So this request will come through into the EC2 control plane. And the EC2 control plane will send a command to the API that we mentioned earlier on the Nitro controller. The EC2 control plane will have assessed, that there's capacity, that there's the necessary resources available on this server to launch this instance. And so the Nitro controller will take this request. It will, of course, validate the authorization and authentication. And then it will reach out across the PCIe bus to issue a command to the Nitro hypervisor to provision out the CPU and memory resources necessary for this instance. The hypervisor will go ahead and do that. They'll initialize that VTD, VTX, the hardware-based isolation features. They'll allocate out the memory. And next, the hypervisor will act back to the Nitro controller, confirming that it has performed those actions. And the Nitro controller will reach out to one of the other I/O-based features of the Nitro Card, instructing them to allocate out an ENI, an EBS volume, and the accordant instance store for this instance type. Those cards will expose out to the BIOS of the main system over SrIOV, an ENA, which is the network interface exposed into the virtual machine, an NVMe device for the EBS volume, and an NVMe device for the local storage. It will then act back to the controller, confirming that it has done this. The controller will then go ahead and let the system know to start up the EC2 instance. The hypervisor will then step out of the way, and in just a little bit, the system will be up. You'll be able to SSH in and manage the EC2 instance as desired. Where things are kind of an interesting quirk that I want to dive into is how all this features with EBS Volume Encryption. So let's say we've got our instance up and running, and now what we want to do is to attach an encrypted EBS volume that's to this running instance. So the first thing we need to do is confirm that our customer, sitting back with their CLI or SDK, has credentials that are authorized not only to perform the action of mounting the EBS volume, but also for decrypting using the KMS key that is used to encrypt that volume. The next few steps will be very similar to what we saw earlier, the control plane issuing out to the cards, etc. But what we'll next find is that the Nitro card receives an encrypted copy of the volume key, which is encrypted by a key that is present only in KMS HSMs. An IAM forward access session is going to be used to allow the control plane to make a time-bound call to AWS KMS on behalf of the customer principal that requested the amount of the volume to obtain a narrowly scoped AWS KMS grant for the key. Now, grants are an identity and access management concept that is somewhat unique to KMS. It's a feature for allowing and delegating out permissions at scale that are narrowly scoped. So let me give you a sense of what that means. This here is the grant, an example of a grant itself. What's really key here are two things, right, is the scoping. So for starters, the principal that is being given the permission to decrypt this volume is a unique principal that is tied directly to the customer instance that's already up and running. So it's this instance. And the context, so the encryption context constraint, applies to a cryptographic link that actually limits the ability to decrypt to only that specific volume. This is not wide-ranging or unconditioned access to a KMS key. It's really allowing only the Nitro system that is hosting this particular EC2 instance to decrypt only this particular EBS volume. So once that grant is in hand, the Nitro card uses that scope down grant. It sends the encrypted volume key to AWS KMS for decryption. AWS KMS decrypts the volume key, and then it re-encrypts the key using a public key that was that's provided for the Nitro card on the system. And it's a public key for which the corresponding private key is available only for that specific server. AWS then transmits the re-encrypted volume key back to the Nitro card over a TLS session, which means that you have actually two levels of encryption on the wire for this data. It's both encrypted directly to a key that is held only by here and by the card, and also in a TLS stream. The Nitro card terminates the TLS connection, decrypts the volume key, loads it into the plaintext key into memory, and the mount proceeds much in the way that we discussed in the earlier slides for the initial instance bring up. So now that we've talked through a bit about the components, we've talked about how they all kind of come together and function, I want to talk about some key resultant security properties of the Nitro system. And the first and foremost is one that I think is particularly and notably innovative. And that is the absolute and intentional exclusion of any mechanism for an AWS operator to access customer data in EC2 instance memory or on the host. As I mentioned earlier, there's no SSH or general purpose access of any kind, not only on the main system board, but also on any of the EC2 Nitro cards as well. All Nitro operations are going to be performed via the secure, authenticated, authorized, logged, and audited administrative APIs presented by the Nitro controller. And there are no APIs presented by the Nitro controller that provide access to this customer data. This is a really, I think, deeply innovative and critically important feature of this system. And honestly, it's a challenge, right? It's an engineering challenge to have done and to have operated. And there are trade-offs to that. We have had to invest deeply in automation and thorough and rigorous testing before deploying, because we do not have a break glass mechanism to log into one of these servers. That said, we believe that this trade-off has been well worth it. It has been the right decision to make for the security of our customers, and we're very, very glad to have done it. At the scale that we operate, our investment in automation has allowed us to truly succeed and achieve some really interesting things that we'll talk about a bit later. But for the time being, I want to cover a few recent developments about this no operator access design that I think are going to be really meaningful for customers. And that's really the efforts that we've had quite recently to provide additional transparency around the Nitro system security design, including this talk, as well as additional assurances around the characteristics of that design. So the first is a release of the security design of the AWS Nitro system white paper. This is a detailed technical review of the Nitro system design and its security properties. The next is our recently released third-party independent architecture review of the Nitro system. It's an assessment that was conducted by the NCC Group, a well-regarded international expert in security. And this report particularly focuses in on the Nitro system design and its support for the claims that we make about zero operator access in the Nitro system. I encourage folks to read this. If you find this topic interesting, and I believe that you probably do because you're here today, it's a relatively quick read, only a few pages long. But for now, I'll give you the quick outcome, which is that the NCC Group found no gaps in the Nitro system that would compromise these security claims. And the last of our recent developments I want to share with you on this topic are the inclusion of language around the AWS Nitro system operator access controls that are so fundamental not only to the Nitro system but to AWS that we included them in the AWS service terms themselves, which is an agreement that we make with our customers. So we're really pleased to have done this, and we're excited to continue our work to share with our customers the innovative developments and security enhancements that the Nitro system can bring to them. So the next topic I want to cover in terms of security properties is that of live update. We're very careful to design every critical component in the Nitro system, Nitro Card firmware, Hypervisor, to be live updatable without relaxing security protocols or defenses in any way. By live updatable, what I mean is that we're able to update these components without impacting customer workloads running on the system. And the important outcome of this capability is that it eliminates the need for any carefully balanced trade-offs around updates and customer impact. We never have to make a choice about customer impact or updating. And this yields improved security outcomes for all users of Nitro-based EC2 instances. Another topic worth covering here is the change management processes for the Nitro system. So there is no AWS operator, no engineer, no matter how privileged, how senior, that can push code to a production Nitro host. We have multi-party review and approval processes, staged rollouts in both testing and production environments, code reviews, security reviews, and automated testing. Then and only then, after proceeding through all of these processes, are binaries able to be cryptographically signed by a private key, which is only accessible through the automated deployment pipeline, and which logs all key signing activity. When we deploy updates out, we do so conservatively, moving cell by cell, carefully monitoring for any perturbations in the system that might be caused by an update, and are prepared and automated for rollbacks if any are needed. Now, of course, if needed, we can move much faster, but in the normal course of business, we prefer a conservative approach. Another topic I want to cover here is passive communications. Now, we saw this diagram a bit earlier, but I want to call out something really notable about it from a security perspective. So we have here the EC2 control plane communicating with the Nitro controller APIs, and the Nitro controller APIs, in turn, communicating with the Nitro Hypervisor. And you'll notice that there's an arrow indicating a directionality of the control flow. The EC2 control plane always initiates communication with the Nitro controller APIs. The Nitro controller APIs never initiate outbound connections with the EC2 control plane. Even something that seems like it would be outbound communication is in fact a polling mechanism. The same is true the next layer down. The Nitro Hypervisor is always receiving communication from the Nitro control APIs, never initiating outbound connections. Because we have well-formed, well-understood communication paths, APIs, and directionality, we're able to alarm and monitor this system for any irregular variance in those patterns and immediately respond to take a system out of service and to call for appropriate action and response. Another topic which is not unique to Nitro, but is probably important for us to talk about just briefly, is to touch upon EC2 side channel protections. Now, in the years following the release of things like Meltdown and Spectre, side channels are of particular importance in the academic research community and for security practitioners, something we want to think about carefully. I'm proud to say that the EC2 approach to tenant isolation and to managing side channels has been conservative and considerate of these types of risks since before those issues arrived. In EC2, we never coalesce memory pages between two customer instances, and we never simultaneously share threads on a CPU or other low-level core attributes between customer instances. Now, in general, the vast majority of our instance types are generally allocated out specific CPU cores and memory which are pinned to that instance throughout its lifetime. There are some exceptions, in the case of our burstable instances, our T-series instances, where we have carefully designed those overcommitted instances such that we can still meet our high security bar for isolation. Right? That means that although an instance might serially execute on the same core over its lifetime that another instance has executed on, they are never still simultaneously sharing threads on the same core or memory page coalescing. We feel that these are very strong protections, and we continue to monitor and engage actively in research in this area and in protections. Eric Brandwein, our vice president and distinguished engineer at Amazon in security, made a really important observation a few years ago on this topic, which is that in the current era of micro-architectural side channels, this topic has become one that is much like cryptography. It's something that is often best left to deep expert teams to manage and address. It's really become an expert topic, and we're very happy and very pleased to be able to employ, resource, and activate some of the world's finest minds in this space. So another topic I want to address here is something called confidential computing. And this is a term that really addresses the concept of protecting code and data while it is in use. So AWS has kind of a view of two dimensions of confidential computing that I want to define and help explain how the Nitro system relates to this topic. So the first dimension of confidential computing is really the isolation between a cloud operator and the data that resides within a customer's instance. The second dimension is a customer who seeks to isolate their own sensitive data and code processing from other portions of their workload. This is the second dimension of confidential computing. Now, at this point in the talk, you will probably not be surprised to hear that the AWS Nitro system is the primary confidential computing technology directed at dimension one of confidential computing. And it is providing that value and that feature to every user of an EC2 instance released since 2018 by default. Now, we also offer something called AWS Nitro Enclaves, which was built on top of the Nitro system and helps to address dimension 2. That's the protection and the isolation among related cooperating workload components, including the protection of the customer's code and data from their own EC2 operators. So what is Nitro Enclaves? Right? This is a tool, a feature that allows customers to build applications that allow them to take confidentiality to the next level. They can isolate their highly sensitive data from their own users, applications, libraries on their EC2 instance. They can do so by moving that processing into a new and isolated, cryptographically attested environment with its own dedicated CPU and memory isolation capabilities. Nitro Enclaves also enables multi-party collaboration, where two or more parties are able to process data without giving access to any of the other parties. They're able to jointly compute on common sets of combined data without ever revealing the underlying data to their collaborators. How does this all work? So Nitro Enclaves are powered by the fundamental confidential computing technology of the Nitro system. Right at the bottom, on a standard EC2 instance, we have instance A and instance B sitting on top of a hypervisor, and they're strongly isolated between each other by the design of the Nitro system that we've discussed thus far. When you add Nitro Enclaves to the picture, you see that instance A has broken off some of its resources, its CPU and memory, handed them back to the hypervisor, and the hypervisor goes ahead and creates a new special purpose virtual machine known as the Enclave. This Enclave is protected and isolated from instance A in the same way that the two, instance A and Enclave A, are both isolated from instance B. The only difference is that instance A and Enclave A have a local channel to communicate with each other that does not traverse the network. So this is a deep innovation in security that the Nitro system has enabled for customers. And innovation is another really key benefit of the Nitro system. Now, when it comes to EC2, right, we have more than 600 instance types available across different operating systems, different optimizations and use cases, and of course, things like different underlying CPUs. AWS, Graviton, Intel, AMD, and even Apple systems are available through the bare metal functionality. The pace of innovation that the Nitro system has enabled us to achieve has greatly increased, right? From the 2017 release of the Nitro system, that rate of innovation has gone up like a hockey stick. The Nitro system really enables us to move fast and introduce new technologies. And it's not just EC2 instances. It's also other foundational technologies. Take, for example, Firecracker, right? Firecracker is a virtual machine hypervisor that runs in AWS in production workloads for AWS Lambda, AWS Fargate, and Amazon Athena on top of EC2 bare metal instances. This system marries the speed of launch, the density and efficiency of container-based workloads with the strong resource isolation of virtual machines. Nitro system has also allowed us to offer UEFI secure boot to customers' EC2 instances, right? This is a legacy technology that can be used to ensure that proper bootloader is signed by a known authority. It allows you to validate that bootloader, and if the validation fails, to fall back to a backup bootloader or stop boot process. That itself also leverages our Nitro TPM technology, right? This presents a legacy and standards-compliant TPM 2.0 into a customer instance. This allows customers to leverage software stacks that expect or require TPMs and provides new and innovative opportunities for things like attestation, storing and generating cryptographic data, and proving platform identity of your EC2 instance. So the Nitro system ultimately serves as this basis for the new innovations and building blocks for confidentiality and privacy on EC2. We discussed things like the encryption in transit between instances, features like transparent and even per VM instance memory encryption, bare metal instances, Nitro Enclave, Nitro TPM, storage encryption, and isolated hardware. To sum things up, here's a few of the points I want to revisit. At the end of the day, the Nitro system, critically, is supporting all EC2 instances since 2018. It leverages a secure boot process based on a hardware root of trust that ensures that every component in this system is signed and every operation is pre-vetted for safety. Every single critical element in the system can be live updated without impacting customer workloads. It provides and enables hardware-accelerated, transparent, line-rate encryption of storage, networking, and memory. Zero operator access exists in the system by design, and it offers a strong and default confidential computing solution for EC2. We maintain a robust conservative and effective tenant isolation approach and an approach to side channels. And the main board itself is completely isolated from the physical underlying control plane network. And critically, lastly, as we just spoke about, is that the Nitro system serves as a foundation and enabler for security innovation across AWS. Thank you all very much for coming, and I'll be actually just outside if anyone would like to chat after the session.